Welcome to the lecture series on learning and control. Today's speaker is Muni Srinivasan Pyadi. He is a PhD candidate in ACE at University of Wisconsin Madison, advised by Professor Varun Jog. Research investigates uh, his research investigates the theoretical limit of adversarial robustness in machine learning and its relation to information theory and optimal transport. Previously, he has worked on statistical learning on graphs with Professor Ambedkar Dukapati at ISC Bangalore. Muni did his BTech from IIT Madras and also worked as an engineer at Samsung R&D Bangalore. I welcome him for the talk, and I will admit the others. I think you have already admitted. So now I welcome Mr. Muni to deliver the talk on the machine learning. And please
Thank
keep
you,
your
Professor
hands,
Patel.
please mute yourself. Okay.
Okay. Right. Hello, all. So this is going to be the first session on machine learning at this workshop. It's an introductory session. So for this talk, I would like to go over some basic concepts in machine learning. First, I would like to go over a quick overview on several types of machine learning approaches that are popular today. And then after that overview, we will delve a bit more deeply into supervised learning in specific. We will introduce the basic components of supervised learning, and then we will discuss linear models. And taking linear models as an example, we will clarify some of the important concepts in machine learning, like bias variance trade-off and regularization. And towards the end of the talk, we will discuss the basics of neural networks and then gradient-based optimization for learning. So in the next talk that will be on machine learning, Ashwin Kalyan will be continuing this deep learning. So this basics of neural networks that we cover at the end of the talk will be sort of a continuation. It will lay the background for the next talk. You can stop me in between the talk also if you have any questions, so that you will be able to follow throughout the talk. You can also, of course, ask me at the end of the talk if you have any lingering questions.
Yes.
Right. For an overview of machine learning, now I would like to define learning as just finding patterns in data, right? Depending on the type of pattern,
মেশিন লার্নিং করতে মনে পড়লো ওরা তো মেশিন লার্নিং এর উপর কাজ করলে প্রচুর মানে ইয়ে পাবে
so depending on the type of pattern that we are looking for and the type of task that we want to accomplish, we can have different types of machine learning. The most popular type is the supervised learning, something that you probably have come across before. In supervised learning, we have a set of training data that is labeled. So we have data points x1, y1, and so on up to xn. And each data point is associated with some label y. So you can think of this as image classification, for example. Given some image, you want to assign it some label. And you have this training data set where you have a bunch of training data images, and each one is associated with some label. And the goal in supervised learning is to try to learn some unknown function f that links each label to the data point. So in the training phase, the algorithm tries to learn some function to predict labels for new data points. And then in the testing phase, we get a new data point x, and the label gives out a prediction y hat. Um, Here it's shown by the symbol y hat. Uh, Depending on the function f that the algorithm learned during the training phase, the testing phase just outputs the new prediction y hat on this test data point. So The common examples for supervised learning are classification. Classification is where the label y is some discrete variable. Like I've talked about before, you can think of this as some image classification example. In image classification, each training data point is some image, and then the label y is some number that indicates what the image is about. Say you want to classify cats or dogs, and cats can be labeled 0, dogs can be labeled 1. Another example of supervised learning is regression. In regression, y is a continuous random variable. So an example for this would be, suppose you want to learn to predict the age of a person given an image of his face. So the face image will be the input and the label will be the age of the person. Next, we have unsupervised learning. In unsupervised learning, the data is not labeled. So here the goal is not to learn some prediction on the data points. It depends on the specific kind of task. So for example, we have clustering. In clustering, the goal is to just divide the data points into similar groups. As an example, you can think of this as Amazon, say it is trying to cluster its users based on the kind of shopping patterns that they have. Maybe among all the users of the Amazon website, maybe some data scientist at Amazon wants to group them into, say, people who are more into fashion wear and people who are more into sportswear, etc. So there is no label that is assigned previously to each data point, but we want to kind of group the points into similar groups. Another example of unsupervised learning is generative modeling. So here what we try to do is learn to generate new data points based on the data points that we have seen so far. So here as an example on the left-hand side, I have shown a collection of images of faces that are gathered from this Flickr Faces HQ dataset. And on the right-hand side is another set of images, but these images are artificial. They are not of real people. These are actually generated by some unsupervised learning algorithm. So what the algorithm has learned to do here is to generate new data points based on the data points that we have provided it. So another popular example of a learning framework is the reinforcement learning framework. I think this is the one that is most closely related to control. Here we have two players. One is the agent or the algorithm, and the other is the environment. And there is some interaction between these two. So agent takes an action and the environment gives a reward. And the goal in reinforcement learning is to learn a policy that maximizes this reward. And this is closely related to some control approaches like Markov decision processes, etc. An example for reinforcement learning will be something like a chess playing. Here, the agent here is trying to play chess with some person. So the opponent combined with the board and the rules of chess is the environment. So agent takes an action, which is just a move in the chess, and then gets a reward, which is how good the move is. So besides these three major types of learning, there are several other types of learning also. For example, there is semi-supervised learning. Here we only have a small fraction of training data that is labeled, and then there is a huge amount of data that is unlabeled. And the goal is still trying to predict the label for future unlabeled test data points. So this framework exists because in practice, usually it is hard to get things labeled. It usually costs money. People have to be employed to manually label certain number of training data points. And usually there will be a huge a portion of unlabeled data points, and you still want to make use of the unlabeled data points. Another framework is online learning. So in the supervised learning framework and unsupervised learning framework that we have seen before, all training data is made available at the start. All training data is available at once. But in online learning framework, the constraint is that training data is made available only sequentially, one by one. So an example for this could be Kalman filter, for example, like for GPS navigation. At any time, you'll only get data corresponding to like that particular state in the system. You won't have like all the navigation data available at the start before training the algorithm. And you have to make prediction at every point in this sequence. So that's the online learning type of learning. Next, we have active learning. Here, the algorithm chooses the data that needs to be labeled. So algorithm gives some X to some oracle or the environment, and the environment provides the label for the data point that the algorithm chooses. So here also, like in reinforcement learning, the algorithm is interacting with someone, and that is a different framework of learning. And next we have adversarial learning. Here, the training data or test data can be corrupted by an adversary with the goal of trying to maximize the error rate of the algorithm. And we still want to robustly learn to make predictions. So in future sessions, I think Ashwin will be talking more about the reinforcement learning type of learning. And then I will also have a session where I will discuss adversarial learning in more detail. Any questions so far? So the next step in the presentation is to go over the basic components of supervised learning in detail. So we will only concentrate on the supervised learning framework. To recall, supervised learning is where you have labeled training data points, and the goal is to make predictions on new test data points. So for the first component, we have this training data that comes in pairs. Each xi is associated with some label yi. We can think of this x as some d-dimensional vectors and y as some scalars. Next, we have some true distribution. Here, we assume that all these input data points are independently and identically sampled from some underlying probability distribution. That distribution is unknown to the algorithm. Similarly, y is again sampled either as a function of x or as a function of x plus some noise, epsilon. So this true distribution is unknown in practice to the algorithm, but the key assumption is that test data is also sampled from the same distribution. So this assumption is basically what provides the link between training data and test data. Without this assumption, we cannot learn anything about test data just by working on the training data. So this is important. Next, we have the learning algorithm itself. A learning algorithm is something that takes as input all the training data points and returns some hypothesis, f hat. A hypothesis is a function that can make that can assign labels to new data points x, maybe test data points. So a learning algorithm returns some f hat, and prediction of the learning algorithm on some input x is denoted by y hat. Y hat is just f hat of x. Next, we have the hypothesis set. Hypothesis set is the set of all possible hypotheses that a learning algorithm can return. So as an example, suppose we consider linear regression. In linear regression, what we do is we try to fit a straight line to the data, the best possible straight line that kind of minimizes the errors. And so in linear regression, the prediction will be something like W transpose times X, where W itself is some d-dimensional vector. And hypothesis set in this case will just be the set of all weight vectors W in this d-dimensional space. Now, another important point here is that we have to limit the hypothesis set in some way to make learning possible. If we cannot just let the hypothesis set be the set of all possible functions from X to Y. So if we have such a large hypothesis set, we cannot learn anything about true distribution just by seeing a finite number of samples in the training data. So an important assumption is in learning is that this hypothesis set is limited in some way. We can discuss it more offline if you are curious. For now, I will move on. We have the loss function next. Loss function is a function that basically says how good a prediction of the F1 algorithm is. So suppose y is the true label of some data point x and y hat is the prediction of the algorithm. Loss function says how different those two are. An example for this is just the squared loss. Squared loss is where we take the difference and then square it. Next, we have the expected loss or the true risk. What this measures is given some hypothesis W, R of W, the true risk, is just the average of the loss across all the true distribution. So here, y hat itself is random because it's a function of x and x is random. And similarly, y is also random. Y is f of x plus some noise, which is random. So taking this expectation gives an average over this randomness. And we want to see how good the loss is as an average over all the data points. This cannot be computed in practice because the true distribution is not known. What we can compute in practice is the training loss. And training loss is simply the average on each of the training data points, the loss calculated on each of the training data points. The goal in supervised learning is to identify some hypothesis that minimizes the true risk. That's this expectation. But that cannot be done in practice because we don't know the true distribution. So in practice, what we do is this empirical risk minimization. So empirical risk minimization is just trying to minimize the training loss instead of the true loss. So here in an example, I have shown this single dimensional data. And suppose the true distribution is some sort of Gaussian, indicated by these yellow lines. And suppose the true data, the training data points, suppose they are these green points that are sampled from this Gaussian. We can fit some straight line through linear regression to these green data points. That is W hat. But this straight line we have learned, it need not be the best for the true distribution. So that is this blue solid line that I have shown, which is W star X. So the hope with supervised learning is that as the number of samples or the size of the data set grows large, this training loss will be approximately equal to the true risk. So if we just minimize this, it might be as good as just minimizing the true risk. So eventually, with very large data sets, we would expect W hat to be very close to W star. So that's the underlying hope. So to solidify the concepts that we have seen so far, consider this example of linear regression in a bit more detail. We have training data. Here I have collected d-dimensional training data points, x1 and so on, xn, in this matrix form, x. So the size of the training data set is n. X is a matrix with n rows and d columns. And each row is a data point in d dimensions. And y is a vector composed of y1, y2, and so on, yn, which just indicate labels of each of the n data points. Suppose the true distribution is some p of x from which these data points are sampled, and suppose y is some f of x plus epsilon. So p of x is not known to the algorithm. In linear regression, we limit this hypothesis set in this way. Hypothesis set only composes of vectors in d dimensions such that the prediction is just a linear combination of w and x. So the only predictions that you're allowed to make in linear regression are this linear type of predictions. Y hat is just W transpose times X. Suppose we consider a squared loss function like before, L y comma y hat is y minus y hat whole square. In this case, the training loss is the average of the squared loss computed on each of the n training data points. Yi minus W transpose Xi whole square. I can write this in a vector form like this using the definition here. Y is a n-dimensional vector, X is a matrix multiplied by the weight vector W, and I'm taking the squared norm for this vector. So for our first simple learning algorithm, we can consider the ordinary least squares. So given some n number of data points with labels, ordinary least squares tries to solve this minimization problem. It forms this matrix Y and X and tries to find the weight vector W such that the squared errors are minimized on the training data. And it turns out that for this goal, we can compute the best possible W hat in a closed form like this. It's just X transpose X whole inverse times X transpose Y. So for a bit more complex algorithm, we can consider this polynomial extension to the linear regression setup. Suppose in this case, we consider a single dimension data points. Each data point is a scalar real number, and X is just the vector of all the n data points, and similarly Y is the labels. And suppose the true distribution is some P of X and Y is some F of X plus epsilon, like before. In polynomial regression, the hypothesis set changes from just linear classifiers to linear curves to polynomial curves. So in this case, our hypothesis set allows for predictions of this form. Y hat can be a polynomial, W1 plus W2 times X plus W3 times X squared, and so on up to WD times X to the D minus 1. So it's a D minus 1 degree polynomial. I can write this prediction again in a vector form like this, W transpose times phi of X, where phi of X just composes of all powers of X. In this case also, I can write down the empirical risk just like before, but instead of W transpose X, I will have W transpose phi of X. And similarly, this is the vector notation for the empirical risk. And just like before, I get this minimization problem. And learning algorithm here, which is a polynomial regression algorithm, it will return a W that minimizes this quantity based on the data set. And in this case also, it turns out that there is a very simple closed form expression for the optimal W hat, the optimal hypothesis that minimizes the training loss. So there is a question in the chat. The question is how to determine the degree of polynomial having only X and Y training data. That is a very good question that leads to our next discussion actually. So please hold on to that question, and if the question is not clarified, I will be happy to discuss it again towards the end of the talk. Right. So now that we have seen two types of learning algorithms, we can talk about this overfitting, bias, variance, and stuff. So in this example here, I have again considered this example of some regression problem in a single dimension. Suppose the true distribution is a second order quadratic. Y is some quadratic function of X plus some added noise. And this is not known to the algorithm. Suppose we use two different algorithms for fitting the data. Here the green points denote the samples that are drawn from this true distribution shown in yellow. And the first algorithm we fit the training data to is this linear regression. We just fit this straight line. And the second algorithm, suppose, is the polynomial regression. That is the red curve. Right? Here, if you notice, the red curve is exactly passing through all the training data points. So for the red curve, the polynomial regression, the training loss or empirical risk is exactly 0. But for the straight line, the empirical risk is greater than 0 because the points don't lie on the straight line. But intuitively, we can see that the polynomial is not a good fit, right? Because if we get slightly different training data, or if we get some test data that is like not on this curve, we will make a very bad prediction on it. So what went wrong here is we were only trying to minimize the loss on the training data points. But as I've shown before, the true objective is to minimize the true risk, the expected loss, the average on the true distribution. So to understand this a bit more, we can decompose this true risk as follows. Suppose we take the squared loss function. R of W, which is the true risk, is expected value of y minus y hat whole square. Y is the true label, y hat is the predicted label. Y is f of x plus epsilon, and y hat is f hat of x. It turns out we can decompose this into two terms. Second term is just the variance of the epsilon noise, and this is called irreducible error because any algorithm will incur at least this much error. This cannot be reduced. But the first term is called reducible error, and this depends on the algorithm that you choose. So we can kind of try to concentrate on minimizing this if we want to minimize the true risk. And reducible error can further be decomposed into two terms, bias term and variance term. Bias says how close your average prediction f hat is to the true function f. So if we take a very complicated hypothesis, like a very higher order polynomial, this bias term will be low because a polynomial can fit any number of data points if we pick like higher order enough. But this second term variance is measuring how much f hat the prediction changes if we change x. So suppose you have slightly different training data point or a test data point that is slightly different from all the training data points. This f hat for a higher order polynomial will be very high because the prediction will change a lot just by changing x slightly. So the lesson here is that if we take a complex hypothesis, like a very high order polynomial regression, that algorithm will have low bias, but it will have high variance. So overall, the expected loss will be high. But on paper, it will look like the empirical risk is very low, so it might be better, but that is not true. On the other hand, if you take a very simple hypothesis, something like a straight line, it will have high bias because it won't be able to fit the true distribution if the true distribution itself is not simple. But it will have low variance because even if we change the data points slightly, even if we get a slightly different version of training data, prediction remains roughly same. So the best hypothesis that we want should be somewhere in between. It should not be too simple, but it should also not be too complex. So this motivates us to somehow correct for this empirical risk formulation by some other term. And that is what I will be discussing next. So that penalty term that I have shown, that I have mentioned before is called regularization. Regularization is basically, all right, so there is a question in the chat. So Tushar asks, are you explaining overfitting and underfitting? Yes, I will be explaining it shortly once I finish explaining this regularization. That's again a good question. It's important that we know about overfitting and underfitting. Right. So in regularization, what we do is we minimize the empirical risk plus some lambda times some penalty term. So this empirical risk tries to reduce bias. This is saying we minimize the loss on training data points. And this regularization penalty, it basically penalizes very complex hypotheses. Like if we want to exactly overfit the data with like lot of polynomial terms, this S of W will be high and that won't minimize the overall objective. For a more concrete example, let's go back to the linear regression setup. So first we had this ordinary least squares where we just try to minimize the squared error on all the training data points. But with regularization, we have this new algorithm called regularized least squares, where we add some penalty term on the weights. So we can have two types of penalty terms which are commonly used. One is the L2 penalty, L2 penalty basically says the penalty is the sum of squares of all the weight numbers in the weight vector. And L1 penalty is the sum of absolute values of the weights in the weight vector. And depending on the type of penalty, we have different types of names. Like if we use L2 penalty, the regression is called ridge regression. With L1 penalty, regression is called lasso. Essentially, what we want to accomplish with this regularization term is that we don't want to overfit the data. We don't want to only try to minimize the training data, because then the variance term will be high. So this is roughly the chart that explains the underfitting and overfitting phenomenon. On the x-axis, we have this 1 over lambda term. So if we consider this underfitting regime, here lambda value is very high. So that means if we are solving for W using this with very high value of lambda, we will pick some W that is very close to 0, because this term will be very high if W is not close to 0. So in that case, the bias will be very high, because there is not much freedom we are giving for the algorithm in choosing W. But variance will be very low, because W is very close to 0. So any prediction you make will roughly be around 0. But as lambda is made smaller and smaller, our bias will reduce, but the variance will increase. And the noise level, of course, remains same, because the noise level, variance of epsilon, that is independent of the algorithm. So when we compute the true risk in practice, we will get this curve, and there is this sweet spot for lambda. In practice, we cannot know this sweet spot because true risk cannot be computed. The true distribution is not known. So we will use some other technique for finding the optimal value of lambda, something like a cross validation. We will get to it if we have time towards the end of the talk. But for now, what you have to remember is when doing regularization, there is some optimal value for lambda. And if lambda is too small, we will be overfitting the data. Overfitting means we have very low bias, but very high variance. And if lambda is on the other direction, too large, we will be underfitting. Underfitting means we have very high bias, but low variance. All right, so that concludes our discussion on the linear models. Next, I will be moving on to neural networks. So if you have questions on the concepts we have discussed so far, maybe you can ask now. In the last few minutes, I will be discussing neural networks.
Hello, could you able to hear me?
Yeah, I'm able to hear you.
Yeah. So could you again explain why variance is most important than the bias? Like why it is important, because we are actually trying to match the function, trying to find out a function how we are going to match with respect to x and y. And you
Yeah.
are saying that we don't need that. We only need the variance to be very small. Why is that?
Right. That's a good question. I would say like variance is not the only term that's important. So what we want to minimize is the true risk, right? True risk has three terms: bias, variance, noise.
Okay.
And over noise, we have no control. So we want to somehow balance between bias and variance. So we want bias to be low and variance also to be low. So if we try to exactly fit the training data points, bias will be low, but variance will be high. So what I mean to say is that we have to balance between these two, because our goal is not to minimize training loss. Our goal is to minimize the expected loss over the true distribution. But this we cannot compute exactly in practice. So we will use some heuristics to do that.
Okay. Thank you.
All right. So we will move on to neural networks. First, I would like to introduce some terminology because these terms, deep learning, deep neural networks, have become really popular in recent times because there have been really successful algorithms for solving all types of learning tasks that I have shown at the start of the talk, like supervised, unsupervised, reinforcement, active learning, online learning. Whatever task you take, these days there is some deep learning approach to solve that problem. So deep learning is essentially the class of machine learning algorithms that use a deep neural network in the core of the algorithm. So here neural network is a connected network of neurons, and neuron is just a mathematical function. I will get to it in the next slide. And a deep neural network is simply a neural network of sufficient depth. So if this connected network of neurons has some depth, we call that a deep neural network. There is no hard and fast limit for how deep it needs to be in order to use the word deep learning. But general sense is that as you go deeper, the algorithms will get better. Um, right. So we will move on to defining some simple neural network architectures. We will start with the neuron. This is the building block for any deep neural network architecture. Neuron is just a function that maps input x in d-dimensional data to some scalar value y. And it does it through this function. So each neuron, it computes the output in two steps. First step is when it takes a linear transformation of the input x. So that is W transpose x plus B. W is called the weight vector of the neuron and B is called the bias. And in the second step, it will take some nonlinear transformation of this computed linear value. And here sigma is called the activation function. Here I have shown two popular activation functions. It's important that the sigma is nonlinear. So sigma of A cannot be just A. It has to be nonlinear in some way. So in ReLU, the full form for this is rectified linear unit. Sigma of A is just max of 0 and A. And for sigmoid, it is this smooth curve that goes from it goes from 0 to 1 as A goes from negative infinity to positive infinity. So bottom line, neuron is just a mathematical function which computes the output of some high dimensional vector x in two steps. First, it takes a linear transformation and then it applies a nonlinear transformation. And the parameters of a neuron are its weight and bias. Now we will define what a feed-forward neural network is. This is a higher level building block in most deep neural network architectures. Usually feed-forward neural networks are used for supervised learning tasks. So a feed-forward neural network is just a collection of neurons that are arranged in a layer-wise fashion. So at the bottom, right. So there is a question in the chat from Rahul who says, is it the same bias as discussed in the regression? That's a good question. It is not. So that bias is very different. Unfortunately, the terminology is such that bias in the context of neuron just means this value here. These both notions of bias are unrelated. This bias just means this particular weight that is connecting this one to the output. That's it. Right. So back to feed-forward neural networks. In feed-forward neural network, at the bottom, we have this input layer, which is just composed of the d-dimensional input vector x. And above that, we have several layers of neurons that are arranged such that each neuron of layer L, say, is connected to every neuron in the layer above it. And in the final layer, we have one or more number of neurons. And the final layer is called the output layer. And the output computed by the neurons in the final layer is just the output y hat of the whole neural network. So the feed-forward neural network, the input is still some d-dimensional vector x, and the parameters are now weight matrices and bias vectors for each layer k going from 1 to L, where L is the number of layers in the network. L is also called the depth that I have mentioned before. So a deep neural network means very large L. So here, the I, j entry of WK is just the weight that is connecting some node I in layer, node I in layer K to some node J in layer K minus 1. It's just that particular node, whatever weight is there on top of it is populated in this matrix like this. And bias Bi of kth layer is just the bias of node I in layer K. Suppose this is layer K and this is node I. Whatever weight is there on this particular edge is Bi of K. So to compute the output of the neural network, we have to execute an algorithm. That's the forward propagation algorithm. What we do here is first we compute the outputs of the first hidden layer based on the inputs. And to compute the outputs of first hidden layer, we have to first take a transformation, a linear transformation, W times H plus B. And then we take a nonlinear transformation, sigma of that A. And we do it successively. So in each step in the feed forward propagation, we take a linear transformation to compute this A, and then we apply this activation function to compute this nonlinear transformation. And we do it in this layer-wise way, and finally we will get y hat, which is the output of the whole feed-forward neural network. So again, feed-forward neural network is just a very complicated function that maps inputs x in d dimensions to some output y. It can be a single scalar value or it can be multiple depending on the number of neurons we have in the final layer. All right, now we will discuss supervised learning with neural network. I think I'm running short of time. I will try to close this in 5 more minutes.
So Muni, I think anyway you have taken the question, so you can go for few more minutes. No issue.
Okay.
In between you have
Thank
taken.
you.
So maybe 10-15 minutes, na? Okay.
Yeah.
Okay.
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 Thank you. Right. Now we will get to supervised learning with neural networks. So again, it's the same setup like we have seen before, just like linear regression. But here the hypothesis set is composed of all possible weight matrices for each layer and then bias vectors for each layer. So instead of just having some W in RD, we have this very huge hypothesis set that's composed of all possible matrices. So here WK has NK rows and NK minus 1 columns. So here NK is the number of neurons in layer K of the feed-forward neural network. So for the loss function, if we are trying to do a regression problem with neural network, the loss function will be something like squared loss. If we are trying to do a classification problem, loss function will be what is called a cross entropy loss. It's just this function. And as seen in the previous slide, y hat can be computed using this feed forward algorithm, the forward propagation algorithm, sorry. So given some weights, given some hypothesis and input, we can compute the prediction y hat using this forward propagation. Similarly, similar to the case of linear regression, we can also add a regularization term for the neural network. So a common regularization term for neural networks is weight decay. It's basically lambda times squaring all the entries in all the weight matrices and bias vectors. So the goal with neural network supervised learning is to learn this set of weights and biases that minimize this very complicated looking expression. We have to minimize this regularization term, the sum of squares of all the weights, and we have to also minimize the loss, average loss on training data points. And each loss depends on this prediction y hat, and y hat is this very complicated looking expression. So of course, there is no closed form solution for this w hat and b hat, like how we had a closed form expression for least squares. So we have to resort to some kind of approximation algorithm for solving this very complicated looking minimization problem. So that brings us to gradient based optimization for learning. Um, we will discuss gradient descent, which is a very simple algorithm. So given some function g of w, goal is to find w that minimizes that function. Suppose there is some quadratic function like this. W hat is the function that is at the bottom of this ball. We want to, with this algorithm, the goal is to find this w. And the way we find it is, we initialize w to some w naught, some point here, say. And in each iteration, we compute the gradient of the function and then multiply it with some scalar, gamma, and then update the weight based on that. So in a single dimension, the gradient is just the derivative of the function. So a derivative here will be like in this direction. So we take steps. In each iteration, we move closer and closer downhill. And eventually, with enough number of iterations, we will reach the minimum. So here I have shown the simple gradient descent algorithm with a fixed learning rate, with a fixed step size. But in practice, what we do is we vary the step size with iteration. A key point is that if the step size is too small, then we will take a lot of iterations to get to the minimum. So that is not optimal. And if the step size is too large, we can actually go away from the optimum. We will not even reach the optimum. And that is also, of course, bad. So we have to choose some learning rate that is just right, not too large, not too small. And a very common trick here is to use a large step size in earlier iterations and then gradually decrease the step size towards the end iterations. And of course, this is not an exact science because we don't know this function like in closed form, right? It's this very complicated looking function here. So if you want to minimize this term and find the weight vectors w, we have to play around with a bunch of learning rates and see what works in practice. And for neural networks specifically, even doing gradient descent is very computationally intensive because in neural networks, the goal is trying to minimize this average of some n functions. So each small function here is the loss computed on some one particular data point. Drawback of gradient descent is that gradient computing takes order of n time because we have to compute the gradient on each of the training data points. And to do each of that requires some other algorithm called backward propagation. And that is a large amount of time just to take one step in the optimization. So what is done in practice is approximating this average gradient by just a sample. So instead of taking this average gradient of all n samples, we just compute gradient on one particular small function, and then we take a step in that direction. So in stochastic gradient descent, SGD, we initialize the vector to some W naught, and in each iteration, we pick a sample from any of the n data points, and then we take a gradient according to that sample only, not compute the whole gradient. And this is more manageable in practice for neural networks. So essentially, the final goal is to minimize this complicated looking loss function that gives us the optimal weight vectors that we can use for prediction in the future. And we do it using SGD, stochastic gradient descent. The algorithm now is that we initialize the weights and biases of the network randomly. And in each iteration, we select a training data point randomly. And then we compute the output of the neural network at that data point using forward propagation. And then we compute the gradient of the loss using backward propagation. And then we update the neural network parameters, the weights and biases, using that learning rate. And then finally, we return the neural network parameters after the iterations are finished. So this is a simple framework for learning, supervised learning with neural networks using stochastic gradient descent. So that is the end of the talk. Here I have a summary of all the things that we have discussed in this talk. First, we have gone over various types of machine learning tasks, supervised learning, unsupervised learning, reinforcement, and so on. Especially reinforcement learning and adversarial learning. We will see more of it in future talks, so stay tuned for that. After that, we have gone over the basic components of supervised learning. And in this discussion, we have discussed some important concepts. The empirical risk minimization, the assumption that there is a true distribution that is unknown to the algorithm. And then we discussed bias variance trade-off. There were a few questions on that, which were good. We discussed underfitting, overfitting. And the important message here is that we are not trying to minimize the training loss. We are trying to minimize the true loss, the true risk. For that, we have discussed some techniques like regularization. We discussed L1, L2 penalty. For linear models, that means ridge regression and lasso. And finally, we discussed neural networks. And then finding the optimal weights for neural networks using approximation techniques like gradient methods, especially the stochastic gradient descent. So that's the end of the talk. If you have any more questions, you can ask now.